Attention, because in this video I'm going to tell you the most important points about Aerospike engines. In case you didn't know, these have already proven to be more efficient, lighter, and simpler than conventional rockets. So the question is, if Aerospikes are so good, if they have so many advantages, how come there isn't a single aerospace company using them today? That's what we're going to talk about in this video. Hello Science Junkie, I'm Sergio Hidalgo, an aerospace engineer, and welcome to this channel. Aerospikes are a fascinating topic. As mentioned in the previous video, when someone sees it for the first time, they can't believe it. So sit down, get ready, because this video is going to be amazing and you're going to understand why aren't Aerospike engines used. Let's see, before we start, let's see what Aerospike engines are. For those of you who have no idea, I recommend you watch the video I'm leaving for you in the corner. For those who watched the video and already know about Aerospike engines, let me go over it again briefly to clarify a few important points. Aerospike engines are a different design from the typical nozzles used by rockets. A conventional nozzle, which is also known as a bell-shaped nozzle, traps the air between its walls. However, what Aerospikes do is allow the ambient air to come into contact with the air that comes out of the engine. What this does is that the pressure of the ambient air acts as if it were a wall, and the process is optimized. In other words, the thrust achieved with Aerospike engines is greater than what is achieved with conventional engines. If you recall my video series on nozzles, I'll include the link in the corner. We always talked about how the most important thing when we're talking about a convergent-divergent nozzle. The most important thing of all is the relationship between the exit area of the nozzle divided by the area of the throat. Once you know that relationship, you know that ratio, you can know what the Mach number at the exit will be and the pressure at the exit. And as we already said, optimal thrust is achieved when the pressure of the air exiting the engine is exactly the same as the pressure of the ambient air, the air surrounding the rocket. But here a problem arose, and that's because rockets launch from sea level and go all the way up to space. Well, the ambient pressure, the atmospheric pressure, decreases from the moment it launches until it reaches space. So they're only going to be optimized for a very specific moment of the journey. However, Aerospikes are completely different in this regard. Because as the ambient pressure changes, and the ambient pressure is what's acting as the wall. When ambient pressure drops, as the rocket rises, the force being exerted on the air coming out of the engine is less, so it's allowed to expand more. So the fictitious ratio of the nozzle exit area divided by the throat area changes as the rocket rises in the atmosphere. This is the most important thing, which we focused on in the previous video, so I won't dwell on it further. If you still have any questions, I recommend you go to that video. Aerospike engines also have another significant advantage not mentioned previously, and that's because the air is coming out from different parts of the nozzle. For example, here you can see it's coming out from the right or from the left. So if you want to achieve vector thrust, you don't need to create a gimbal that rotates the rocket and directs the flow's exit. You could simply reduce the amount of air coming out from one part of the engine. And that would create a difference in thrust between both sides and cause a rotation. I mean, you could rotate the rocket simply by increasing the power on one side compared to the other, and that would greatly simplify the rocket's design and manufacturing process. But now for real. If it has so many advantages, how the heck is it not being used today? Well, there's one main reason, and really it's just one. I mean, there's only one reason that brings all of this down. It's true that there are some other slightly smaller things behind it, but the main reason is the issue of cooling. Let's get to it. At first it might seem counterintuitive, since if you look, we're replacing a wall in the divergent part with air, the ambient air. You don't have to cool that part. But really, what we're actually doing is taking it away. We're taking one of the walls of the pipe and putting it on the other side. So that really has nothing to do with it. Also, in a convergent-divergent pipe, the pressure along the pipe decreases, but so does the temperature. Therefore, the temperature in the divergent part is much lower than in the throat or in the convergent part. Therefore, the real cooling problem actually appears in the throat and in the convergent part of the nozzle. Because due to the nature of Aerospike engines, the throat of an Aerospike engine will always be larger than the throat of a conventional engine, as long as you want the amount of air passing through both engines to be the same. So for the same amount of air, the throat of an Aerospike engine will always be larger. This is easy to see because if you look at a conventional bell-shaped nozzle, well, we have a circle and the air passes through that circle. However, in an Aerospike engine, the air passes through a cylindrical ring. That's why I said in the previous video that it's very important to understand what we're looking at when we see a diagram of an Aerospike engine. Because when you see the typical two-dimensional images, like the one I was showing you before, you have to remember that it's actually a three-dimensional body of revolution. It's not actually that easy to see. So, this is where the problem comes in, because both in the convergent part and in the throat, we have a cylindrical ring. In the convergent part, it's a ring that gradually narrows. The problem is that there, we have two walls to cool. If you look at the cylindrical ring, we have the inner circle and the outer circle, and both have to be cooled. You can do some calculations very quickly so you understand how much the surface area you have to cool increases with an Aerospike engine. Don't worry if you get lost with the numbers, I'll group them for you later, but I want to explain the process for those who want to follow along. I suppose you do, since honestly, the channel has a pretty high level, so I guess most of you can follow along. Imagine having a throat that's 50 square meters. That's an incredibly large size for a throat. But let's talk in whole numbers. I mean, I don't want to get into 0.003 square meters because then it would lose its meaning. So let's talk in whole numbers. Well, yeah, imagine that. A throat about 50 square meters wide. In a conventional bell-shaped nozzle, the air would pass through the entire circle. So we would have pi times r squared, which would have to be equal to the 50 square meters. And from there, we could easily solve for the radius and know what the radius of our throat would have to be. Well, when we solve for it and do the math, we get a radius of 3.9 meters. But, however, if we now had an Aerospike engine where we wanted the inner wall to have a radius of 3, for example, we would calculate the radius of the outer wall. Knowing the formula for the area of a cylindrical ring, well, by substituting the radius of the inner circle as 3 meters and knowing that the area of the ring has to be 50 square meters, we get a radius of 5 meters for the outer radius of the cylindrical ring. And with the results obtained with the radii, well, I'll group them for you so you can see them. Well, for example, here we would have to cool the surface of the wall, which would actually be the same as the perimeter of the circle. The formula. The formula for the perimeter of the circle is 2 times pi times r. For the bell-shaped pipe, we would have to cool about 25 meters of perimeter, but when we now compare it with the cylindrical ring, the difference is huge. The perimeter of the inner circle comes out to about 18 meters, while the outer circle comes out to 31. So we would have to cool the 18 meters of the inner circle plus the 31 meters of the outer circle, which is about 49 meters. Compared to the 25 of the bell-shaped nozzle, I think you can already get an idea of where the problem is. Although this doesn't mean that it's impossible to build an Aerospike engine. Of course it's not. Aerospike engines have been built and tests have been done with Aerospike engines. What happens is that in the end, well, they've realized that it's not profitable because a lot of complications arise just to be able to cool the walls. But I'm convinced that in every project where they want to design a rocket from scratch, they have this idea of an Aerospike engine from the start. So they would probably do an analysis of how much more an Aerospike rocket costs compared to a bell-shaped rocket. Knowing that, of course, the Aerospike engine is going to give you better performance later on when you want to do a launch. We're not just talking about cost in terms of money or new systems you have to add for cooling and so on. No, we're also talking about weight cost. Because remember, the heavier your rocket is, the less you'll be able to put into orbit. But anyway, there are other secondary factors that go against Aerospike engines, like the one I'm about to tell you right now. And the thing is, actually, it hasn't been a single Aerospike rocket that has been used operationally that has actually made it. Out of the tests, out of the trials, there isn't any. To make a bell-shaped rocket, you already know the step-by-step process, including what authorities will require for certification. It's like having a pre-written script that you simply need to follow. But with Aerospike engines, it's not like that because there hasn't been any yet, so we don't know what problems might come up from things we haven't even considered yet. And in the end, this means that when you're in doubt between the two, you just go with the bell-shaped engines. It's a bit like what happens with airplanes. All airplanes have the same shape, and there are a lot of people who say that you could make airplanes with different designs and they would be more efficient. Well, probably, but you would have the complication of having to introduce the new technology and get it accepted. You would have to be the one breaking barriers, and in the end, that's going to be expensive for you, and that's why Aerospike engines aren't used. Although, to be fair, it should be mentioned that there is a company that is using them or wants to use them called Aerospace. I've actually been getting a bit interested in the projects they're working on, and I think they deserve a separate video. Let me know in the comments below. What do you think? Are you interested in me talking to you about this project? I've sent them an email to get in touch with them so that, well, I can make a really good video. Besides that, it's also worth mentioning that one of the proposals to replace the space shuttle was actually a good one. It was an Aerospike engine used in the Lockheed Martin X-33. But well, because of cost issues and the usual things in engineering, in the end the space shuttle wasn't replaced. I'm making a video about that fascinating project because it's incredible and really interesting. I think it's necessary on this channel so that the Spanish-speaking community is well informed about what the space shuttle really was. With these two videos, we conclude the Aerospike series, although it wasn't much of a series since it only consisted of 2 videos. I think that with the 2 I've made, you can perfectly understand how they work and why they're not used. And I think this represents 100% the magic of engineering. Just because one design gives you better results than another doesn't mean it's better, because you have to take into account the extra costs that might come up with that design. For example, a lot of people ask me, hey, why don't commercial airplanes have, for example, the ability to take off vertically? Why don't planes have huge parachutes so that they can land safely if something happens? It would be incredible if it could do that, but it would make flying much more expensive. And I'm 100% convinced that they've done those calculations for every crazy idea they've ever come up with. And in the end, they've seen that it's not profitable. I don't know. People also ask about thrust vectoring in commercial planes, but it's unnecessary. It serves no purpose. Sure, you'll have more maneuverability, but is the cost you're going to generate worth it just to have a little more maneuverability? It's not worth it, and that's why it's not used. And well, moving on from that, leave your opinion below about Aerospike engines. Do you think they're really going to be useful in the coming years? We'll see. Probably many of you think they will, probably many of you think they won't, no matter what you think. Let me know in the comments below. I'm really interested in hearing the opinion of the science junkies. You know, it's been a pleasure spending this time with you. If you enjoyed this video, give it a big like, subscribe if you haven't already, and watch this video next. You know, as always, above all, science first.